Hello, welcome to another in a series of videos on solving first-order differential equations. In this video, I will be talking about linear first-order differential equations and how you can solve those. In a previous video, I talked about what makes a differential equation linear, ways of classifying differential equations, including classifying them as linear or nonlinear. And in particular, if we're talking about an order 1 differential equation, if it's linear, that means it can be put into the form something times dy dx plus something times y equals something, where each of the somethings is an expression involving x. It can be as simple or as complicated as you want, but it can only involve the independent variable x, not the dependent variable y or its derivative. And here I am assuming that we're using the letter x for the independent variable and y for the dependent variable. If you're using different letters, so you have a dy dx term, you have a y term, and you have a term that involves neither of those. But you don't have y squared, y cubed, the cosine of y, or anything else like that going on with y. And if you can put it in this form, you can take whatever the a of x stands for, whatever the coefficient is on dy dx, and divide through by that, and put it in the form where you just have dy dx by itself, plus something times y equals something. So the method of solution that we're going to be looking at here, step 1 is always going to be to get our equation into this form. Then step 2 is going to be to take that equation and multiply through by an integrating factor. Now, an integrating factor is kind of what it sounds like. It's a factor that if you multiply by that factor, you get something that you can integrate. So in this particular case, what we want for an integrating factor is going to be e to the integral of p of x dx. That is, we look at the coefficient function in front of the y, find an antiderivative of that with respect to x, and all we need is just one particular antiderivative. So we don't need to mess around with a plus c or anything like that. Just find an antiderivative of that thing in front of the y, and then take e to whatever you get for the antiderivative. That's your integrating factor. Notice that once you've got that integrating factor, if you took the derivative of that integrating factor with respect to x, this is what you would get. Remember, the derivative of e to the x would just be e to the x, but putting that with the chain rule, the derivative of e to the something would be e to the something times the derivative of the something. So here we have e to the something, and the derivative of the antiderivative of p of x would be p of x itself. And so if we take our equation that's set up like this, and we multiply both sides by our integrating factor, here's what it looks like. We have e to the integral of p of x dx times dy dx, plus e to the integral of p of x dx times p of xy, equals e to the integral of p of x dx times q of x. And look at what we have going on the left side. There's two terms here. One of them involves y, the other involves the derivative of y. One of them involves the integrating factor, the other involves the derivative of that integrating factor. Does that remind you of something? That kind of pattern there where you've got two things and each has one thing times the derivative of another thing? That's the kind of thing you get when you use the product rule. So that entire left side of the equation happens to be the derivative of the integrating factor times y. First thing you get is that integrating factor times the derivative of y, plus the second thing you get is the derivative of that integrating factor times y itself. So you are going to be able to easily anti-differentiate that left side. Meanwhile, the right side is some function of x. It's some expression, maybe really simple, maybe really complicated, but it's just going to depend on x. So you're going to want to anti-differentiate that with respect to x. And that will give you your solution. So this method is conceptually pretty simple. In practice, actually working through it with a particular differential equation might be really easy, or it might be really difficult, depending on how easy or difficult it is to find the antiderivatives that we need to find. But it's all a matter of how good you are or how able you are to do the integration that comes up. So let's look at an example. Let's solve the differential equation x plus 3y times dx plus x dy equals 0. And first I'll notice that this is not separable. It's not an exact differential equation. It does have homogeneous coefficients. The coefficients on dx and on dy are both homogeneous of degree 1, so we could take the approach to solve it that I described in a previous video about when you have homogeneous coefficients. But it is also a linear differential equation. It's got a y, it's got a dy. It would be a little more obvious that it's linear if I divide through by dx. So I'm going to want to put it in the form that I'm used to working with. First, if you divide through by dx, you get x plus 3y plus x dy dx equals 0. Then I'm going to rearrange things so that the dy dx term is first, and then the y term is second, and then the stuff that doesn't involve y is over on the right. So x dy dx plus 3y equals negative x. And now I don't want anything in front of the dy dx, so I'm going to divide everything on both sides by that coefficient, x. So then I have dy dx plus 3 over x times y equals, and of course negative x divided by x would be negative 1. So it is in the form dy dx plus something times y equals something. Now, step 2 is to find the integrating factor. We do that by finding an integral or an antiderivative of the coefficient on y, that function of x that y is being multiplied by, and then taking e to whatever that turns out to be. So our integrating factor here would be e to the integral of 3 over x dx. Well, an antiderivative of 3 over x would be 3 times the antiderivative of 1 over x, so 3 times the natural logarithm of x. And remember, we just need one particular antiderivative, so I don't need to mess around with a plus c, and I don't really need the absolute value bars around the x. Now, 3 times the ln of x is equivalent to the ln of x to the third power. That's one of the basic properties of logarithms. And then the e and the ln undo one another. They're inverses of one another. So e to the ln of x cubed would just be x cubed. So that's the integrating factor, x cubed. Step 3, now that we've found that integrating factor, we are going to multiply everything on both sides by that integrating factor, x cubed. So x cubed times dy dx plus x cubed times 3 over xy equals x cubed times negative 1. And simplifying that a bit, that's x cubed dy dx plus, and then we got a 3, and the x cubed divided by x is x squared, so 3x squared y equals negative x cubed. Now, once we've done this, the left side is guaranteed to be the derivative of the integrating factor that we multiplied through by times y. In this case, that would be x cubed times y. Because if you product rule that, you get the first thing times the derivative of the second thing plus the second thing times the derivative of the first thing. You get x cubed times the derivative of y plus y times the derivative of x cubed. So that's going to be easy to anti-differentiate. The antiderivative of the derivative of something is just the something. So now we're all ready for step 4, where we anti-differentiate both sides. The antiderivative of the derivative is just x cubed y, and the antiderivative of negative x cubed would be negative 1/4 x to the 4th plus c. So we're pretty much done, although if you want your solution given explicitly with y on one side equal to some function of x on the other side, that's easy enough to do here. Instead of something times y, if we want y by itself, just divide both sides by the something. So if I divide through by x cubed, there's what y is equal to. Y is equal to negative 1/4 x to the 4th plus c all over x cubed, or we can separate that out into negative 1/4 x plus c over x cubed. And if you want to check that, this is what we got for our solution. The solution to this differential equation is supposedly for y to be the function negative 1/4 x plus c over x cubed. And if that's what y is, then the derivative dy dx would be negative 1/4 plus, and now I'm thinking of this as c times x to the negative 3, so the derivative of that would be negative 3c x to the negative 4. So if we stick that into the equation, we've got dy dx, negative 1/4 minus 3c over x to the 4th, plus we got 3 over x times y itself, which was negative 1/4 x plus c over x cubed. Multiply that out, and we got negative 1/4 minus 3c over x to the 4th, minus, and here the x over x cancels, and this would be 3/4. And then when I multiply 3 over x times c over x cubed, I get 3c over x to the 4th. So one of these terms is a minus 3c over x to the 4th. The other is a plus 3c over x to the 4th. Those two add up to 0. And the rest is a negative 1/4 minus 3/4, which together adds up to minus 4/4 or minus 1. So the left side is equal to the same thing the right side is equal to, negative 1. That checks out. That is the solution to that differential equation. Okay, I do have a couple more examples to show you so that you really get the hang of how this works, but I'm going to end this video right here and then come back in part 2 and show you a couple more examples.